Morning. Okay, we'll go ahead and get started. Can the people on Zoom hear me and see the screen?
Yes.
Thank you. So I do have a couple of announcements before we get started on the material today. And that is, we were scheduled to have a quiz on Thursday, this Thursday on Chapter 11. That has been moved to next week on Tuesday. And I wanted to tell you why that's being moved. So this week on Thursday, and this week in general, the Webster is bringing in candidates for a new faculty member in the chemistry department. And so the interviews are this week, and one of the things they're asking candidates to do is to give presentations to classes. And so on Thursday, the 2 sections of Gen Chem that I teach, you're going to get another person lecturing you through Zoom. So for those of you who are in the room with me, thank you for being here. But on Thursday, you don't need to come in, just dial in through Zoom to see the presentation because the candidates are going to be remote. And so I'm not certain what they're going to lecture on. It may be something we had last semester, maybe something that you get this semester, but it'll give you an opportunity to see potential candidates or candidates for this new role in chemistry. And the other thing is you'll be asked to evaluate the candidates. So whichever candidate you happen to get for this section, they'll give a presentation, something associated with one of the general chemistry topics, and it'll give you an opportunity to give some feedback on how you thought that person did in terms of lecturing and just presentation and the whole thing. So please try and dial in for that. It's your opportunity to have some input on who a new faculty member may or may not be in the fall. And so I'd appreciate it if you could do that. I know I'm gonna dial in to see the people as well. So that's the reason why we're doing the shift. I'm expecting today to get more detailed information about which candidate it will be for this section and the Zoom information and all that. When I get that information, I will post it on Canvas. So as usual, please check Canvas, periodically to see if there's any changes or anything with this class. Any questions about that? So, okay, so just to repeat again, this Thursday, you'll have a guest lecture. That'll be one of the candidates that the university is interviewing for a new chemistry faculty position. And then it's your chance to kind of see one of the candidates and give some feedback on that person. As a result of that, our quiz on Chapter 11 will be next Tuesday. So it's scooted back. Because of this, as you can imagine, there's some shifting in the schedule overall. So I have posted on Canvas an update of the lecture schedule and exam schedule and all that. So if you want to see how things have shifted from the original syllabus schedule, please go onto Canvas and look at that announcement, and it has the updated one on there. So I'm sure it won't be the last change that we have. I didn't think it would happen quite this soon. Usually it lasts a little bit longer than that, but that's okay. We'll just adjust and go on from there. So thank you again for spending some time evaluating the candidate and giving your feedback. Like I said, it's a good opportunity for the students to have some input on who might be one of their teachers in the future. So today what we're going to do is we're going to start on Chapter 12, and Chapter 12 talks about solids. So solid materials. And one of the things I wanted to mention is one of the chemistry professors here, Professor Groneman, this is his area of specialty. So he does a lot of research in the area of solids, so crystal structures. If you talk to him about crystal structures, he loves them, he'll get all excited. So what I would say is, as we go through this material today and then next week, if the crystal structure stuff, you think, gosh, this is kind of neat, I like this, then I would strongly encourage you to talk to Professor Groneman and see if you can do some research with him in his lab. If you look at the crystal structure stuff and say, I hate this, I never want to see it again, that's okay too, but then you probably don't want to work with Professor Groneman. You want to pick a different advisor. But he's an expert in the area, and he also is doing stuff much more advanced than what we'll be talking about here. So even if you want to just know a bit more about it and would like to know a little bit more in terms of advanced crystal structure stuff, he's a great person to talk to. So anyway, and he did not pay me to say any of that either. All right, so let me go ahead and so what are we talking about when we talk about solids? There's a few things in general that I want to mention. One is that you find that solids, especially the crystalline solids, have a lot of structure or order to them. We talked a little bit about order on that last chapter, but here we're really going to talk about it a lot. And when people are looking at solids and looking at that order, that really, depending upon what type of order it is, it gives you a feel for some of the physical properties that the solids might have. And so when we're looking at the interactions that are involved with solids, there's four main types that we'll talk about in this chapter. And I'd like to just first go over the general idea behind these types, and then we'll get into some more detail on what that means exactly. The other thing I'll mention is that this chapter, in my opinion, is a very visual chapter. There's some math and there's some calculations that we'll go over, but there's also a lot of visualization of it and visualizing things in 3 dimensions. And so I would strongly encourage you to spend some time looking at the book and looking at some of those figures that they have in the book, because the pictures are pretty good there, and making sure you kind of understand how the atoms fit together and some of this structure that we'll be talking about, because it can be a bit abstract. I know for myself personally, I have to really think about this stuff to visualize it correctly in my head. And so once again, I would really encourage you to spend some time looking at the pictures in the textbook to make sure you understand what we're talking about when we're talking about the crystal structures and things like that. So, okay. So one of the areas that we'll talk about are metallic solids. And metallic solids, as you can imagine, involve metals. And what's unique about the metallic solids is that the valence electrons are delocalized. And so delocalized is just another term for shared. So the electrons around those metal atoms aren't just sitting there on each of the metal atoms. They kind of spread out amongst all the metal atoms in that matrix and in that solid material. And it's usually referred to as a sea of electrons. And so remember, when we talked about metals last semester, we said metals are things that like to donate electrons, right? They tend to have positive charge. So as these electrons kind of move away from it, it creates this sea of electrons. And because of that, you have this sharing of valence electrons, and you get some properties of metals. Metals are pretty good at conducting electricity. So in other words, moving that charge through. And then the material also is pretty strong and usually not brittle. And think of just some metals that you're aware of. So think of, one I always think of is copper wiring. So copper wiring is pretty strong. You can bend it, you can twist it. To cut it, you got to really get something sharp to cut it with. And it's what a lot of our electrical systems are. So it really carries electrons, carries electricity well. So we have the metallic solids, and we'll go into more detail on what those look like in a little bit. The next one is ionic solids. So when we think ions, we think cations and anions, and that's what we're talking about here in ionic solids. And so because of that cation and anions in those ionic solids, we have that electrostatic attraction. Remember, that's our old thing of opposites attract when it comes to charge. Positive charge likes to attract negative charge and vice versa. And so some properties that come out of this are that it doesn't usually conduct electricity, those solids don't, and they tend to be brittle. Probably the one example of ionic solids that always comes to mind for me is table salt, sodium chloride. And if you think about that, if you have some big chunk of table salt, some of that more coarse salt, you can crush it. It's real brittle. And so you can crush it and it kind of splinters off. That's an example of an ionic solid, and we'll talk about how those cations and anions interact in a little bit. The next one I want to talk about and mention is covalent network solids. So remember we said before when we were talking about bonds and bonding, that covalent bonds are really strong. And in that case, we were talking about the atoms within a molecule. Well, you can also have in solids covalent bondings, what they call a covalent network. So you can have one atom bonding to another in this network of atoms. And that network of covalent bonds, you think of all these covalent bonds kind of linking together, results in the material being really strong, really hard. And two examples of this, one is diamonds. So normally when people think of diamonds, they think of, oh, they're pretty and they're jewelry and things like that. But diamonds also have value because of industrial uses of their really good cutting tools and things like that, because they're so hard. And the other one is semiconductor materials. And we'll talk about that a little bit later in the chapter. But semiconductor materials, those are materials that are used in the electronics industry. And you think about electronics as you're kind of moving electrons around, and we'll talk about how that happens in this covalent network type of solid. And then the fourth one I want to mention is molecular solids. So with molecular solids, we actually have discrete molecules. So we have molecules, and they're held together by some of those weaker forces that we talked about last chapter. And so remember last chapter, we talked about dispersion forces, dipole-dipole interactions, and hydrogen bonds. And so those were those intermolecular forces that we discussed where we said that's how things are associated. We see that's also in molecular solids. In last class, I had a question about this, so I'll ask you the question is, what are we talking about when we talk about dipole-dipole interactions? Does anybody remember that from last week? Yes.
Isn't that when there's two dipoles and they kind of align themselves to be like a negative or positive end?
It is. So that's when you have the two dipoles, partial negative, partial positive, and then you have the negative positive alignment, like you said. But what causes the dipole? Do you remember that?
It's polar.
It's polar. What causes polar? There's a word I'm looking for. Anybody on the Zoom? Can you remember the word? Anyone on Zoom? What property? So if I'm trying to figure out if something is polar, I want to know, is it electronegative? Because remember, electronegative, we said, means it kind of pulls the electrons towards it. And that's where we said we tell if something's electronegative by looking at that periodic table. To the upper right-hand corner, so like fluorine, for instance, oxygen, nitrogen, those guys up in that upper right-hand corner, those are more electronegative. So you need something that's electronegative to create that dipole. And if it has a dipole, then we say it's polar. So those are all kind of interrelated. It's all kind of the same thing, but it's that electronegativity that we're interested in. So in these molecular solids, they're going to be held together stronger if they have some polarity to it. They have those electronegative atoms. And remember, we said hydrogen bonding was stronger than dipole-dipole, which is stronger than just the dispersion forces. But compared to some of these other things that we talked about, they are still relatively weak. And what that means from a physical perspective is that that material tends to be physically softer and it has lower melting points. So those are four main types of solids that you can have based on the interactions that are present. And so here, this is your first taste of the visual of this topic that I was mentioning. And so we see examples of metallic, ionic, covalent network, and molecular solids. And when you see things like this, each of the balls represents a different atom, and then just how they kind of fit together. So think of it as kind of like a puzzle. And I just want to point out on the covalent network one down here on the left, you see these covalent bonds between the atoms, whereas the others, they're just kind of snugged up against each other. And it's that network of bonding on the covalent network ones that make those materials so strong. And you see two examples they have are carbon, which would be the diamond, and then silica, which would be the semiconductor material. There are two other types of solids that we'll talk about. And the first one is polymers. And so polymers, that's just a chemistry name for plastics. So if something's some type of plastic, it's a polymer. And when you talk about polymers, what you're talking about is usually pretty high molecular weight compounds. It's usually a chain of some type. And by chain, I mean repeating units. So there will be some base structure in the compound, and then that just repeats itself, repeats itself, repeats itself. There's also something called a copolymer, which would be two different units repeating themselves. But the key is polymers are big molecules, high molecular weight molecules, and they're also repeating either one unit repeating over or two units repeating over. They're covalently bonded, and some of them have some of those intermolecular forces between some of their groups to each other. On the slide, we say that it's stronger, more flexible material. That's sort of true. There are a lot of different types of polymers out there. Polymer chemistry is a big area of study. And so some polymers are strong and flexible, some aren't so strong, some are brittle. It just kind of depends on the properties of the polymer. You know, one example of that I'll give you is you think of the water bottles, that disposable water bottles that come. You see all the time on the news, they show the oceans with the water bottles polluting, and that's a big problem, and people are trying to figure out what to do. Well, if you think about that, that's a case of where that's strong, flexible material, but we probably wish it wasn't so strong. You know, in a perfect situation, you would have that water bottle where it's strong enough to hold the water, and you can transport it, and you can drop it, and it doesn't break and all that. But what you would like is that it then, maybe after a year or so, it degrades and decomposes into something that's harmless. So that's one of the things that people work on in polymer chemistry, is figuring out what properties do you want in the material and what properties don't you want, and then can you make a polymer that does that. The other type of solid that you often hear about, and we're going to talk about, are nanomaterials. And so these are crystalline compounds again, but the crystals are really little, 1 to 100 nanometers. So that's pretty small. A nanometer, remember, is 10 to the minus 9th meters. So that's really small. And that small size gives them some different properties than larger crystalline materials. So we'll talk about those two types a little bit more later. When we talk about solids, I said earlier that structure is a big deal. And so whether you call it structure or organization or whatever, what you're talking about is having, in crystals, having a set physical geometry of the atoms or molecules. And what you typically have is you have repeats of that. And that's what gives it this ordered, this crystalline type of look. And so when you have the order with this repeating pattern of atoms or molecules, that's called crystalline. And that's what we're really going to focus on, is the crystalline side. There is another type when you don't have this structured arrangement, and that's called amorphous solids. And so those are actually very different from the crystalline solids in that they don't have this structure or this repeating type of pattern. Once again, Professor Groneman, he studies the crystalline solids, and that's what most of the solid study centers around, actually, is the crystalline ones. So in order to talk about these, there's some terminology that you're going to have to learn. And that's what we're going to go over now. And so some of these are terms that you're going to hopefully you'll memorize and then understand what it means. And this gets into, maybe you may have to look at some of the figures in the book in addition to the slides to just get comfortable with what we're talking about when we use some of these terms. The first term I want to talk about is something called unit cell. And so the unit cell is the basic shape of the repeating unit. And so it's a unique arrangement of atoms, and then that arrangement gets repeated over and over and over, and that helps you wind up having the structure. So, excuse me, so the structure of a crystalline solid, remember we're talking about crystals here. Structure of a crystalline solid is defined by the size and shape of the unit cell, okay, and we'll show you some examples of that in a little bit. And also the locations of the atoms within the unit cell. So you have a fundamental shape of that unit cell, and then you have where the atom is located within the unit cell. You'll get a geometric pattern of points of how these unit cells are arranged, and this arrangement is called the crystal lattice. So if you think about what a lattice is just in general, not talking about chemistry, but a lattice, is this arrangement of a repeating pattern. And that's what we're talking about here. And that's what we're talking about in the crystal area, is that we have this shape, and then it repeats over and over. That repeating shape is the crystal lattice. Within that lattice, there's a unit cell, which tells us how those atoms are arranged. And we're going to take a look at some of those examples. We're first going to look at it in 2 dimensions, and then we're going to look at it in 3 dimensions. 3 dimension is what is going on within that crystal, but we're going to look at 2 dimension first, because it's just a little easier for most people to visualize 2 dimensions than 3 dimensions. And 2 dimensions just means it's all in one plane, it's on the piece of paper. When we get to 3 dimensions, then we have that third plane that kind of comes out of the paper. When we look at that structure of the crystalline compound, there's something called lattice points. And the lattice points are the meeting points, and you'll see a picture of this in a moment, of that unit cell. And so the key is that each lattice point has an identical environment, because they're all interconnected. And so it's the same thing over and over. We'll talk about something called lattice vectors. And so a vector, as you may remember, and you may know if you had physics, has both direction and magnitude. And so those lattice vectors are what connect the lattice points and define the unit cell. So we'll have, for those vectors, we'll have direction, and then we'll also have magnitude. And we'll get to those in a moment. So once again, we're going to talk about, just to go back, we're going to talk about a unit cell, which is that repeating unit for the arrangement of the atoms. We're going to have a crystal lattice, which is how all those unit cells look when they're put together. And then we're going to have lattice points, which kind of show the connecting points for the unit cells within that lattice. And we'll describe that with the lattice vectors, which have direction and have magnitude. So let's look at some two-dimensional lattices. So on these figures, the black lines are the lattices, okay? So we see oblique lattice, square lattice, rectangular lattice, hexagonal lattice, and rhombic lattice. So if we look at hexagonal, it's this hexagonal shape that is the lattice. The parts that are color shaded, so kind of like most of them are like a lightish blue, there's one that's a little bit light green. Those are the unit cell. So the unit cell for these last two, the hexagonal and the rhombic, are a little different than what the actual lattice is. Couple things that I want to point out on here. So let's take a look at the first one, the oblique lattice. And we see one vector is A, another vector is B, and so we have direction with the line and the arrow, and then we have a link. So we have direction and we have magnitude with that. We also have an angle between these two vectors, which is gamma. So when we describe these things, and you'll see this on each of these that we have information about A and B. So in other words, the magnitude of those vectors, and we see that for the oblique one, A and B are not equal. So one is bigger than the other. When we go to the square lattice, and A and B are equal. That's what you would expect. The square, all the sides are the same. And then you kind of go on down the line and you see for rectangular, they're not equal. Hexagonal, they are. Rhombic, they are. The other thing that you see is that we get information about that angle between the two vectors. So for oblique, it can be different values. But for the square lattice, it's always going to be 90 degrees, rectangular 90 degrees. The hexagonal is going to be 120. The rhombic's a little different because we actually have two versions of what we can have. And so that one can vary. So this description of the unit cell centers around the vectors. In this case, since it's two-dimensional, A and B, and then the angle between those vectors. So takeaway here is the black grids that you see with those shapes, that's the lattice. And then the light blue or light green within it, that's showing us the unit cells. The problem with this representation is it's only two-dimensional. And we know that solids aren't two-dimensional, they're three-dimensional. So what we want to do is we want to expand this, now that we've gotten a little bit of feel for what we're talking about, into that third dimension. And then it gets a little more complicated. And so let's take a look at the 3D crystal lattices. And there's 7 of those. So this is something I would expect you to know, okay? And so in these, I want to just point out here on the left, we're seeing that we have our A and B vectors and our gamma, which is the angle between A and B. But now we've added that third dimension, that C vector. So now we've got 2 planes that are on the page, so to speak, and one coming out. So now that's where our 3D comes in. With that 3D, we not only add one vector, but now we get 2 other angles that we have to be concerned about. Beta, which is between A and C vectors, and alpha, which is between B and C vectors. So for these 3-dimensional lattices, we'll use the vector information about A, B, and C, and also the angle information around alpha, beta, and gamma. So let's just take a look at some of these. So the first one is cubic. As we might imagine with the cube, the sides are all equal and the angles are all 90 degrees. Tetragonal, we see A and B are going to be equal, but C is not going to equal A and B. And so of course we have this longer side because of that. But the angles all stay 90 degrees. Orthorhombic, we see that A doesn't equal B, doesn't equal C, so those vectors are all different, but the angles stay at 90 degrees. Rhombohedral, A, B, and C are the same, but we start seeing some changes away from that 90-degree angle. So that gamma angle no longer is 90 degrees, while A and B are the same. Hexagonal, we have A and B are equal, C is different, and we're back to 90 degrees for A and B, and 120 degrees for gamma. Monoclinic and triclinic, those get a little different. We start to see kind of this little wobble to it, and we see differences there in terms of vector and associated bond angles.
Question.
Yeah.
Can you explain the difference between tetragonal and hexagonal?
Okay, so in this one, the difference is this gamma, this one here it's 90 degrees, here it's 120, so it's opened up wider. It's a little hard to see, but it's like this angle here, that's opened up wider. It's not like this,
So
it's like that.
So like the top and bottom would not be a square, correct?
Right,
Okay, I see that.
right.
I see.
It's hard to see this stuff, at least I think it is.
Yeah.
And that's why I was saying, for me, I have to look at this stuff more than I should admit to really visualize it. And we'll see even more. Right now, we're just looking at one unit. Okay, when we start putting multiple units together, I think it gets even a little more difficult to visualize. And that's where I think it really, you just have to kind of look at the pictures for a while until you get it. Because I know for me, I have to look at them a little bit. Any other questions about these? This is one time where it would be nice to have a bunch of toys where you could, play with it and see it. Okay, there's a couple other things about lattices that I want to mention. And there's also two other kinds where you get primitive lattices, and there's two types of lattices, primitive lattices and centered lattices. So primitive lattices have it only at the corners. So lattice points only at the corners. So you have these dots in this primitive cubic lattice that are on the corners of that cube. That's a primitive lattice. You can, however, have an atom somewhere else. And the two types are the body-centered cubic lattice. Once again, we're talking about the cubic lattice here, where you have lattice points on all the corners, but also you have one right in the middle. So you have an atom right in the middle. And then face-centered cubic lattice. So what that means is you've got the 8 that are on the corners, and then you have 6 sides to that cube, and there's 1 on the middle of each side. Okay? So the primitive, you just have the points on the corners of the cube. Body-centered cubic lattice, you have the points on the corners of the cube, and then one that's sitting kind of, think of it as floating in the middle. And then you have the last one, the face-centered cubic lattice, where you have the 8 corners, and then on each of the sides, in the middle of the side, you have 1 there. Okay, so just when we think we got everything figured out, it's always going to be on one of these lattice points. Sometimes you do have it where the atoms are not on lattice points. And so here's an example of what I mean by that. And when we say it's not on the lattice point, it's called a motif. And so here's an example of a unit cell here on the left. And in between, we see two atoms bonded to each other, but yet neither of those atoms is sitting on the lattice point on the corner. If we go to the next diagram from that single unit cell, and we see what it would look like if these cells were all in a lattice configuration, we start to see that there's a pattern there. But still, none of the atoms fall on a lattice point. So none of them are on one of those corners. But what you start to see is in the third diagram, and you can kind of visualize it in the second one, but in the third one they show that you get atoms from neighboring cells having some type of bond with the other. And so then you see this hexagonal type of repeating pattern when you start having the bonding from one of the unit cells, atoms in that, to an atom in the unit cell next to it. And there you can, if you step back and look at that, then you see how if it has the ability to do that bonding, you really can get some structure there. Remember that we talked about, that's what this is all about, getting structure. And that's the kind of thing you might see in diamond or something like that, where you get this structure forming one thing with another. Okay, there's a little bit of homework associated with this first part that we covered. Go ahead and take a look at that, and the answers are posted on Canvas if you have any questions. I'm going to move on and start talking about metallic structure. So remember we said there's metallic, there's ionic, and a couple others. We're going to go through some of these now in a little more detail. And the first one we're going to do is metallic structure. So, as I said before, with metallic metals, with metallic structure, we have those valence electrons that get delocalized throughout the whole solid. That's that sea of electrons we mentioned. And so you've got that. And so we're going to talk a little bit about that and what that means. When we talk about metallic structure, we tend to have one of three types. We have primitive cubic lattice, the first one, body-centered cubic lattice, and face-centered cubic lattice. So the metals tend to be cubic lattice type of structures. And so remember we said body-centered, well, you have an atom in the middle. We said face-centered, you have atoms on the faces of the six sides. And then primitive, you just have atoms on the corner. So in this second row here, we see that primitive, body-centered, and face-centered cubic lattice, what that looks like. At the bottom, what we see is now we're drawing using the balls to represent the atoms to give us more of that three-dimensional, fuller look. And inside of that, inside of each of these drawings, what you can see is we have drawn the first one what that primitive lattice is, the second, the body center, so we have got the points on the corners and then one in the middle, and then finally the face-centered cubic lattice where we have the 8 lattice points on the outside and we have points on the face of each of those 6 sides. And what that does is that gives us a feel for how this second row kind of fits in when we actually have the atoms represented. The other thing I want to just mention is the last one that has the red, one of the atoms in red. That's not meant to be a different atom, it's just to highlight that when you have an atom like this, a corner atom, which is what that is, it's shared by 8 unit cells. So in other words, these corners, that atom is part of 8 different cells. So in each cell, only 1/8 of that atom is part of that cell. So in general, as I said, when we have a corner atom, 1/8 of it is within 1 unit cell. If it's an edge atom, 1/4. If it's a face, 1/2. And then finally, if it's in the middle, it's the whole atom is within that cell. So we use this kind of information to figure out how many atoms are within that unit cell by seeing, is it shared or not? And if it is shared, how much is shared? Here's more of a 3-dimensional kind of cutaway view of this, what we just talked about of that sharing. And so if the atom's on a lattice point, is usually not totally within that cell. And you can determine how much it is by kind of looking at how the sharing goes. And so in this first one, we see a primitive cubic metal. And what you see is it's got the 8 atoms there. So on each of the lattice points, each of the corners, but then it's cut away. It's been cut away in order to show you how much is just in that unit cell. And if you go ahead and look at it, what you see is that each of those corners, only 1/8 of it is in that cell. If we then go and look at the body-centered cubit, we see we have those 8 on the corners, but that one in the middle is kind of protected in there. It's not coming to any of the edges. So we've got a whole atom in there. When we go down to face-centered, we see, once again, the corners being 1/8, but then the faces on each of those sides is basically cut in half. So what that means is if we go back, and that's a visual of what we said here, face is shared by 2, so it's a half. 8 share the corners, so that's 1/8. The one in the middle is all by itself, that's 1. We can use that information to see how many atoms per unit cell. So the first one, 8 times 1/8 is 1. The second one, we have 8 times 1/8 again, and then we have 1 in the middle. So that's a total of 2. And then the third one, the face center, we have 8 times 1/8 for the corners, and then 6 times 1/2 for the middle one. So that's a total of 4. So what we use this information for is when we're trying to figure out how many atoms are in that unit cell and what volume that would be. We can figure out densities, things like that. So does it make sense talking about first primitive body-centered and face-centered cubic lattice, the arrangement of the atoms there? Then in that unit cell, we're saying that if it's a corner, it's shared by 8 and it's 1/8. If it's edge, it's 1/4. If it's face, it's a half. It's in the middle, it's 1. And then the third thing is just a repeat of that, but kind of looking at it more with this 3D representation that we have on the right-hand side. Okay, any questions about any of that? Okay. So now, we've been looking at kind of the unit cell and things like that. Well, now the other thing that happens is these crystals pack. Okay, and there's 2 ways that we'll see packing. The first is the cubic closed packed, and hexagonal close packed. So CCP and HCP. We've got some figures here, but to be honest, these aren't the good ones. The good ones are the next slide. So I'm going to skip to that. And we're gonna visually look at what we mean by the two types of packing. I will point out one thing. On this top, where it says side view, you see AB for the hexagonal close pack, and then ABCA for the side view of the cubic close pack. We'll talk a bit about what that means, the ABAB and the ABCA. But what we're going to do now is we're going to look at the layers of how these atoms are packed, and you're going to look at it like you're looking at it from above. So you're on top of it and you're looking down on it. Now let's go over the hexagonal close pack, the one on the left first, and then we'll do the other, the cubic one. So right now, this first picture on the left, we see the balls which represent our atoms, and you'll see some coloring of red or yellow in the spaces between them. So those atoms are packed together as closely as they can be, okay? And then we have some space in between them. Remember, we're looking down on this. So then the next thing we're going to do is we're going to take another set of atoms, and we're going to set them on top of there. Okay, we're going to kind of wedge it in there so it fits nicely. And what you see is, when we look down now, we no longer see the yellow markings. That means one of these atoms, one of these balls, is sitting down in that yellow indentation part of that first sheet of atoms. We still see the red though, right? So we've covered up the yellow places with this sheet of atoms that we've placed down. And now we can't see that gap, that open spot, but we still see the red because of how we put that in there. Let's go to the third layer. We're taking another set of atoms and laying them down. What do we notice? We notice that we still see the red, okay? So what that means is those must have been put down in the kind of the light colored gaps that we see, that fit down on there. And so we can continue doing this pattern of the first one, then putting the second one down, we put this one down again, and that's that ABA pattern that we mentioned. Okay. Let's look at the cubic and see how that differs. So we start with the exact same thing, okay? So this first one on the hexagonal and this first arrangement on the cubic, it's exactly the same. What's going to be different is how we place things. And so now we place our second layer down. Well, let's compare the two. Both of them, we have the light colored openings, and we still see the red. So the second layer that we put down is exactly the same for the cubic as it was the hexagonal. And that's this AB. It's when we get to the third layer that we see a difference. So when we did the hexagonal, we put that same layer down as we started with. Well, now let's look at the third layer. What do we see? We see kind of a light colored openings, but we don't see that red anymore, okay? So what that tells me is when we put down this third layer, instead of putting it in the light colored openings in the second layer, those atoms are fitting in to the openings that have the red. And so this layer, this third one, is a different type of layer. So that's why it's ABC, and the other one is ABA. So we have the same on the first layer, same on the second layer. The third layer of the hexagonal, we went back to what we did on that first one, but in this second one, the cubic close pack, we have a different arrangement there. And if you look at these bottom figures here, the side view figures, and you see these dotted lines that are drawn, you can see how they're different of how they go up through that. And that's another indication that the arrangement of those atoms is different. Okay? So this is now, we're really getting into this multidimensional stuff. First, we started with 2-dimension, just flat plane type stuff. Talked about lattice a little bit. Then we started talking, expanded up into the 3-dimensional lattice. Now we're talking about not only the lattice stuff, but now we're talking about layers and how that fits in. So as you can see, these crystalline solids can get pretty complicated pretty quickly. You've got all this different geometry and fitting together and stuff like that. So I'll say it once again, I think with this chapter in particular, it's good to spend some time looking at these pictures, making sure you're clear in your head what's kind of going on in terms of how the stuff fits together and all that. Okay, any questions about this stuff? All right. So there's a term that we use called coordination number. And coordination number is the number of atoms immediately surrounding a given atom in a crystal structure. So as we said, that cubic closed packing has an ABC stacking pattern. Hexagonal has AB. In both of these, each sphere has 12 equidistant nearest neighbors. So 6 in the same layer, and 3 above, and 3 below. And it's that number of atoms, as I said, that immediately surrounds the atom in that crystal structure that is the coordination number. So what you can do is you can go back and look at some of these and see if you can count up to get to this 12 equidistant spheres around each atom. Okay, so as we talk about metals, there's something called alloys. And alloys are when you have more than one element in the metal. And people do that in order to give the metal some different properties. And so by having different combinations of materials with the metal, you can get some different properties in terms of corrosion resistance or strength or things like that. And here's a few examples of some alloys. And I'll point out a couple of these. So one is bronze. I think most of us have heard of bronze. Bronze is actually 88% copper, 12% tin. Stainless steel is another you hear about a lot. Stainless steel is over 80% iron with a little bit of carbon, a little bit of nickel, and then 18% chromium. So stainless steel, though, this is one version of stainless steel. There's a lot of different versions of stainless steel where they vary the ratios of these components. And one of the big things for stainless steel that they worry about when you change this about is for corrosion reasons. And so corrosion could be chemical reactivity type corrosion or any other kind, but stainless steel has this combination to make it withstand weather, to withstand chemical reactions, things like that. And then the third one I'll just point out is, sometimes you hear people talk about sterling silver. Well, sterling silver is only about 92% silver, the rest is copper. So it's not pure silver. That's why if you have something that's sterling silver, you don't get as much money for it if you take it into a place to sell precious metals as it would be if it was pure silver. Because it's not all silver, and someone would have to do something to get rid of the copper to get it down to silver. There's a few other examples on there which you can take a look at, but these alloys are real important because in the field of metallurgy, they figured out that by doing some tweaks to things, you can give it better properties than the metal has by itself. So when we talk about alloys, there's 3 types of alloys. One is something called substitutional alloys, and that's where a second element takes the place of a metal element. So in this case, you have gold and silver mixed, and that's where you start getting to some of the carat gold type things. And there's an interstitial alloy. That's a case of where you have your structure of the metal itself, and then you're able to put other things in kind of the gaps, so to speak. In this case, they're putting some carbon in there. And then the third is heterogeneous alloys. And that's where the components aren't dispersed uniformly. In these first two, you disperse them uniformly. In the third one, we look at this electron micrograph, and you see iron metal up to the upper left, iron with some carbon doped into it down the bottom right. And so where that comes into play a lot is in the field of catalysis. Metal catalysts are pretty common in organic chemistry to make reactions go faster or better. And the metal tends to be pretty expensive. So people will dope it with carbon or something like that, or use carbon as the support and dope it with the metal in order to make an alloy that's less expensive. So substitutional, interstitial, and then heterogeneous alloys are three types of alloys that you get with metals. There's one other thing, and that's an intermetallic compound. So this is not an alloy, this is an actual compound that has multiple components to it. So because of that, it's very ordered. The negative is it tends to be more brittle than the substitutional alloys. So for me, I haven't seen much of this. We've seen quite a bit of these alloys like this, especially the heterogeneous ones, where people intentionally dope things in. So we've been talking about our sea of electrons with metallic bonding. And so here we have a figure that kind of represents that. The positive atoms or the metal atoms, we see kind of the sea of negative charged electrons, those valence electrons that are kind of floating around all these in our lattice. And remember, we said that metals like to have more of a positive charge. That was one of our things. They like to donate electrons. And so this kind of fits in well. The electrons have an electrostatic attraction to those metal cations. Once again, that's our opposites attract when we're talking about charge. So electrons are negatively charged. The metal atoms tend to have a little positive charge to them, so you have that attraction there. But the idea is that the electrons are distributed throughout this matrix, and that's where that term, that sea of valence electrons comes from. Because of this, metals have properties in terms of conductivity, in terms of malleability, which means just bendability, and things like that. And that's where this sharing of electrons, kind of a group share thing, comes into play. So if you recall last semester, one of the things we talked about was molecular orbital theory. And molecular orbital theory was where we talked about how you have bonding and non-bonding orbitals, which help explain what goes on a broader perspective, not just the atomic orbital perspective, but more broadly across the molecule. Here, since we're sharing all these electrons, molecular orbital theory comes into play. And so what we know is that as we go to more electrons in the atoms, the melting point increases. So in this plot, the bottom graph is period 4, the middle one is period 5, and then the top one is period 6. So as we add more and more electrons to the situation, we see that melting point increases. And so that makes sense. You've got more electrons, you've got more interactions, and this is where we use molecular orbital theory to help explain some of this. So you probably thought you were done with molecular orbital theory, but we're going to talk about it a little bit more here. So just to refresh your memory, when we talk molecular orbital theory, a few points. One is the atomic orbitals combine to make molecular orbitals, and these molecular orbitals extend over the entire molecule, okay? So we go from that bonding atomic orbital type model we talked about to this whole molecule molecular orbital model. The molecular orbital can contain 0, 1, or 2 electrons, and then the number of molecular orbitals equals the number of atomic orbitals that combine to form molecular orbitals. We know that if we add electrons to a bonding molecular orbital, that it strengthens the bonding. If we add them to the anti-bonding molecular orbital, it weakens the bonding. Remember, we had bonding molecular orbitals, anti-bonding molecular orbitals. We fill those bonding molecular orbitals first, then we start filling the anti-bonding. So if we have full bonding molecular orbitals, we're in good shape. We got something that's pretty stable. We start adding electrons, they go into the anti-bonding molecular orbitals, and then things start to break down and it gets weaker. So let's use some lithium atoms to illustrate what we're talking about in this molecular orbital approach. So here on the left, we have lithium. It has 1 valence electron, and we see that represented. Then we go to 2 lithium atoms. Well, now we have, since we have 2 atoms, each with 1 atomic orbital, we have 2 molecular orbitals. One is the bonding, the other is the antibonding. So the bonding is the lower one, lower energy one. The antibonding is the higher energy one, the reddish people. We see we have 2 electrons, those fill into that lower orbital, that bonding orbital. We go to 4, so now we're going to have 4 molecular orbitals, 2 bonding, 2 anti-bonding, and we fill those electrons. Once again, that's pretty good, that's pretty stable. We put 2 electrons in the first one, 2 electrons in the second, nothing in the anti-bonding, so we're good to go. We keep doing this, and then we get to 20-something lithium atoms. And you think, well, how do you get to 20-something lithium? Well, this gets to our matrix, right? Or lattice. And so now what happens is this gets less distinctive. And so you have what's called a band of molecular orbitals. First, the bonding, then the anti-bonding. And you're going to fill the bonding ones first, and then you fill the antibonding. So just like you do on these lower ones, but except now, it just gets a little harder to pick apart the distinct levels, and you just kind of treat it more as a blur, so to speak. More of a continuum. The other thing I want to point out is when we talk about metals, and you think about where they're at on the periodic table, we're starting to get where metals usually have d and p orbitals. So you get more of these electrons than you do with some of the lower atoms on the periodic table. And so as you get to those more electrons, this whole molecular orbital theory gets a little more complicated, and we'll just kind of leave it at that. Okay, any questions about any of that stuff that we went over? Okay, what I'd like to do is go over a couple of the homework problems that I've asked you to work on for this section. Let me get that out. Okay, so the first one I'd like to look at is 1235. And in this one it says, iridium crystallizes in a face-centered unit cell that has an edge length of 3.833 angstroms. So when we say edge length, what are we talking about? Yeah.
That'd be a vector.
It is, yeah. So edge length is just when we have that unit cell, what's the distance from one of those last points on the corner to the other, right? So yeah, it's one of the vectors. And so what that is important about that is if we want to figure out a volume of the cell or something like that, volume of a cube is that number cubed, right? Length times width times height. And we know those are all the same from that chart that we had in the beginning that said for the cube, those three are the same distance. If you don't remember all that, that's okay, but that's what it's telling us. And so here, the first question they have for us is calculate the atomic radius of the iridium atom. So we're told it's a face-centered cubic, we're told the edge length, and there's a formula actually that tells us how edge length relates to the radius, and that's this formula here. A, which is the edge length, equals 4 times the radius times the square root of 2 divided by 2. Here's the math to it, here's the cosine of that, but we'll use this formula there. So for a face-centered cubic cell, which is what they told us this one is, that's the formula we use to have a relationship between edge length and radius. So in that case, we can plug in our values. We have that 3.833 angstrom value. We're solving for radius. So then the next step would be to divide both sides by 4. We divide them both by 4 and we get 0.95825 times the radius equals the radius times square root of 2 over 2. So once again, make sure you know how to use your calculator to do the square root of 2 divided by 2, do that correctly. And then you would do that math, so divide each side by square root of 2 divided by 2, and you get 1.355 angstroms for the radius. What's an angstrom? Do you remember the units on angstroms? So angstrom is 10 to the minus 10th meters. So you'll want to remember that. And why am I saying that? Because on part B, we're going to need to know that information. And that's something that you would be expected to know. So in part B, they're asking us, calculate the density of iridium metal. So when I say density, the first thing that should pop into your mind is mass per volume. Okay, that's the definition of density. I think last semester that might even have been on the final or something, I don't remember. But mass per density. So if I'm talking mass, I'm usually talking grams or something like that. If I'm talking density in terms of the volume, a lot of times I'm talking milliliters, right? Well, we're talking about shapes and cubes and things like that. So milliliters really isn't the way we think of stuff like that. Cubic centimeters is, though. And remember, centimeters cubed is the same as milliliter. Okay, those are interchangeable. So in this case, we know that face-centered cubic has 4 atoms per unit cell. How do we know that? Because remember we said if it's face-centered cubic, that it's got 1 on each of the corners, and those are each an 8. So there's 1. And then we've got that half of 1 on each side. That's half times 6 is 3. So there's a total of 4. So we know we have 4 atoms in this, okay? We know that our edge length, we were told that in the first part, is this 3.833. Okay, so if we know what that edge length is, then that's in centimeters. We'd want to change that to centimeters. Then if we cube it, this length times width times height to get the volume of a cube is what we would do. That would give us centimeters cubed, so we'd be in the right units for that denominator. So what we're gonna do is, we're gonna take that 3.833 angstroms, change it from angstroms to meters. This is where I was asking you, 1 angstrom equals 10 to the minus 10 meters. Then we're gonna convert that to centimeters. 1 meter equals 10 to the second centimeters. And now we've converted our 3.833 angstroms into a centimeter value. 3.833 times 10 to the minus 8 centimeters. So we've got our bottom part of this density figured out. Okay, we're gonna cube that, and we'll have centimeters cubed. In the top part, we got 4 atoms. We knew we had 4 atoms based on the geometry of this, right? And we talked about that earlier. So 4 atoms, if we want to change atoms to grams, that's where our old friend Avogadro's number comes into play. So 4 atoms, we know there's 6.02 times 10 to the 23rd atoms in a mole. Okay, that's our definition of Avogadro's number. Once again, something hopefully you're remembering. And then we can change moles into grams by using the molecular weight. So now, from a units perspective, we have our numerator in grams. We have our denominator, because we cubed this centimeter value into centimeters cubed. Grams per centimeter cubed, grams per mil type thing. That's a density, a normal type of density value. And then it's just a matter of doing the math. And we get 22.68. So does everyone see kind of the logic that we went through on this? We had to use a few pieces of information. On the first one, part A, there was a formula that we had to pull out of the book that was given to us, okay? And that was for a face-centered cubic cell. Then we were able to find the radius there by just doing the math and hopefully having our calculator buttons doing that correctly. The second one on this face-centered cubic, we had to go back and figure out how many atoms were there. And we could do that by knowing how on those different lattice points, how much of it is shared. And we got to a value of 4 based on what we know about how those corners are shared and the faces are shared. And then we had to think about, if we're talking density, we got to wind up in mass per volume. Since we're kind of talking space and cubes and stuff like that, that's where that centimeter cube thing comes into play. Length times width times height. And then we're in atoms, we want to get from atoms to grams. Whenever we want to get from atoms to grams, that's where Avogadro's number comes into play. That allows us to do some of those conversions. Okay. Let's look at the next one. So in this one, in 39, they're telling us that aluminum metal crystallizes in a face-centered cubic unit cell. How many aluminum atoms are in the unit cell? Well, this is similar to what we just did. If it's face-centered, then we know we have atoms at the corners, right? We have the 8 corners. Each is an 8, so there's 1. We have the 6 faces, there's 1 in each of those. We know those are shared at half. So once again, 1/8 times an 8 is 1, 1/2 times 6 is 3, total of 4 atoms. Then it asks us what the coordination number is. We know the coordination number is how many things are next to it. And for this configuration, we know we have 6 in the same layer, and then we have 3 below and 3 above. If you don't agree with that or believe it, go and look at the photos and see if you can count them up and see where you get the 6 in the same layer and 3 above and 3 below. This gets back into that how they fit together thing, all right? And then in C, it's another one of these where, for this configuration, we're trying to figure out either the length of the side or the radius. In this case, last one we were given the side length, this one we're given the radius. So in this case, we would plug the radius here in our formula for R, and then solve, and that would give us that length in angstroms, or we could convert that to centimeters if we wanted to. And then finally, the last step, where we want a density, should be similar to what we did on the last problem. We know there's 4 atoms. We use that Avogadro's number to convert it into molecular weight values, to convert the top into grams. We wanted to take our side value and get it into centimeters. And then we cube that to give us centimeters cubed. And our density would be grams per centimeters cubed. So what we did here is kind of a repeat of what we did in the other one. So it's a similar thing. So this is a type of calculation you should be comfortable doing. And thinking about kind of the logic, because you've got a few things going on. You got to figure out how many atoms are there. That goes back to that, what type of unit cell is it, and things like that. Understanding that radius and length of the unit cell, how that relates. And then finally, using that type of information to calculate out what a volume would be. Or their density would be, sorry. Okay, so just to repeat again, Thursday, you'll have the guest lecture. Once I get the Zoom information, I'll put it on Canvas. Would appreciate if you could dial in. For those of you in class, don't come to class on Thursday, just dial in remotely. And the quiz will not be this Thursday, it'll be Tuesday of next week. All right, thank you.